You are so lucky because now we get to talk about standard normal random variables. Standard normal random variables. They're called standard normal random variables because they're sort of standardized. Oh, they are. Standardized normal random variables. That's what they are. Okay, so a standard normal random variable, z, this is the typical notation that we use for a standard normal. Okay, when you see a big Z in this business, when you're doing probability and statistics, the big Z is typically reserved to indicate that you're talking about a standard normal random variable. Standard normal random variable is just a normal random variable, except it has mean 0 and standard deviation 1. So if you flip back a few slides here to the density function, remember, we aren't going to really worry about this, but if you set standard deviation to 1 there, and 1 right in there, and mean is 0, then what do you get? You get 1 over root 2 pi e to the negative x squared over 2. And flip back, it's exactly this, 1 over root 2 pi e to the negative, well, z squared over 2. You replace the z with an x, and there you go. It doesn't matter what the argument is there, but we'll use a z here because we're talking about standard normal. Anyway, remember, you don't have to know this stuff, okay? But if you know something about functions, or maybe a little bit about calculus, then good for you. This is exactly the function that describes this curve, which is the standard normal curve. You can see it, right? Because there, it's centered at 0, has standard deviation 1. See that? And this should make some kind of sense because, we've talked about standardizing data sets before, right? Like if you have a dot plot, some data over here, okay? What happens when you standardize it? Well, the point pattern stays the same. All you wind up doing is, the net effect here is that it just shifts it down around 0. So it's recentered at 0, and it compresses or contracts or stretches it out about 0 so that its new standard deviation is 1. And you can see that, the end result here, no matter what you start with for a normal curve, it looks like it's done exactly that. It's centered about 0 and the standard deviation is 1. We'll get to some examples here, but these standard normal random variables are important for theoretical reasons and for computational reasons too. We'll be using them when we get more into statistics, especially when we make inferences for proportions. Okay, so if I want to find these probabilities, it should be no surprise that you just use your calculator. The mean there will be 0, standard deviation will be 1. Okay, now it turns out if you leave off these last two arguments, your calculator knows that you're dealing with a standard normal. Okay, so you can just do it like this, but if you leave off the mean and standard deviation there and you just do normal CDF parenthesis a comma b close parenthesis, then it thinks the mean is 0 and the standard deviation is 1. Okay, what's the relationship between standard normals and other normals? So glad you asked. So if x is some normal random variable with mean mu, I don't know, like 100, something that's not 0, and standard deviation sigma, something that's, say something different from 1, then if I standardize it, guess what? If I take x, this normal random variable, subtract off its mean and divide by the standard deviation, I get a standard normal, right? The end result is you get a normal distribution with mean 0 and standard deviation 1. Okay, that is, if I want to know the chance that this random variable x, let's say this is the behavior curve for x. This is the curve down here that describes the behavior of x. So on the average, it's here. Sometimes it's over there. Sometimes it's over there. But usually it's right in here. X is distributed normal, so it behaves according to this curve, this normal curve. It has some mean mu, I don't know, maybe it's negative 50, standard deviation is maybe like 10. Well, if I standardize that variable by subtracting mu and dividing by sigma, then what happens? It's now centered here at 0, centered at 0, and it has standard deviation 1. So then the probability that x falls between A and B is the same as, if you standardize every piece of this, well, we sort of skipped a step in here, but there's sort of a hidden step there, would be the probability A minus mu over sigma is less or equal to x minus mu over sigma is less or equal to b minus mu over sigma. Okay? All you're doing is standardizing every piece of this expression, right? If you do the same thing to every piece, that's a completely legal move. You haven't violated the inequality there. But now the thing to notice, though, is that if I take x minus mu and divide it by sigma, if I take this normal random variable x, subtract its mean and divide by the standard deviation, that thing behaves like a standard normal. Okay? So we just replace it with that z symbol there, and then all of this stuff here is the same as that, and all of this stuff here is that. Yeah, so let's get rid of all this mess and clean it up. So what does this give us? Well, the end result is that if I know the mean and standard deviation for some normal random variable, and if I want to calculate probabilities for it, then I can just use a standard normal. In fact, this is the way we used to do it. Back when I was in school, we didn't have these fancy calculators that would like make your breakfast and stuff. We had to use these things called normal tables. It looked a lot like this. Got all these numbers in them and stuff. You may have professors along the way that insist that you look these things up in normal tables. If you do, then grin and bear it. But you need to know that nobody does it like that anymore. If you get a job and you've got to get normal numbers, or these little z numbers, or compute normal probabilities, and you use one of these tables that's truncated here to the, say, the rounded to the third or fourth or whatever decimal place, you'll get sent home. That's right, you'll be out of work, because nobody does that anymore, because we have software that'll do it super fast, much more accuracy. So in this class, we'll use our calculators. Now here's something else that you need to know. This has to do with percentiles, okay? Percentiles, z sub alpha notation. Now this can be real hard or it can be real easy. A lot of people get tripped up on this, but there's no reason that you have to, okay? Everything you need to know is right here in this picture, okay? All this pretty much says it all. This curve right here is that of a standard normal. It's centered right here at 0, has standard deviation 1. Now, if I draw a line right here, vertical line right there, see that line? Then if I want to talk about the area to the right of that line under the standard normal curve, and I give it some name like alpha, okay? Alpha, we spell our Greek letters with English letters. Alpha, you spell it like A-L-P-H-A, right? Area also begins and ends with A. Alpha begins and ends with A, so maybe it's no coincidence, so we'd like to use alpha for that. If this area is alpha, then this mark is called z sub alpha. Z sub alpha, okay? That's the symbol we give it. Z sub alpha, because we're putting a alpha there down in the subscript. Z sub alpha. What's the meaning of that mark? Well, if you think about it, if I've got alpha to the right there, then I've got 1 minus alpha off to the left. Right? No, left. Right? No, left. Oh, I mean, you know what I mean. I've got alpha over here, and I've got 1 minus alpha over there. Okay? So what does this mean? If I take 1 minus alpha and multiply by 1, or, 100%, that's this mark, that z sub alpha number, that is the 1 minus alpha times 100th percentile for this standard normal distribution. I know all this seems pretty crazy, and you're probably wondering why in the world do you have to know it? Well, we're going to need it coming up when we make confidence intervals and do hypothesis testing. As a quick example here, what if this area here was like 12%? Well, then this mark, we would say, is z sub 0.12. Okay, which is the same thing as the 88th percentile. I'm going to shorten that because I'm running out of room. Perk. The 88th percentile. Makes sense? It's because I've got 88% over here. If I've got 12% over here to the right of the mark, I've got 88% over here. See, when I was in college, there was this great restaurant down the way called New York Cafe. On Friday nights, I would order one of their great calzones. Best spinach calzones. Put lots of cheese in there, and those calzones would arrive, and they would look something like this. It looks sort of like a normal curve, except they didn't go off forever in either direction, although sometimes I really wish they had. They had these ends on them. My dog and I would sit there and watch TV. I always like to give him a piece. I like to give him about 25%. Now, if these calzones had been shaped like rectangles, that would have been pretty easy for me to figure out, right? Probably wouldn't even have to get a ruler. I could just, eyeball. There's half, so, quarters probably look about like this. So I'd lop this much off and give it to him. I'd take out my knife and I'd cut it right there. But instead, they didn't come that way. They came this way. So the question was, gosh, if I want to lop off 25% to give to my dog, where do I draw my knife through? Okay, well, it would be easy if 50%, it's probably about there. Where's 25%? It's not halfway between this mark and the end, right? Because halfway between there and there, this is not 25%. This much is less than that much. Okay, so I really need to move my knife further in to the left. Okay, so how do I do that? Gosh, it was a real problem on Friday nights. I'd put the knife over here, and my dog would start growling at me. And I'd put it over here, and he'd start wagging his tail, and I'd say, no, 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 no. Okay, so where do you put your knife, right? Where do you draw your knife through to lop off, the top 25% or alpha? It's really the same kind of question, right? So if this was a normal, a standard normal, okay, and it's centered here at 0. The question sort of becomes, if this is 25%, 0.25, then all of this stuff, I'll shade it in orange here, all of this stuff down in here is 75%, 75%. And so now this mark here, this mark is my 75th percentile, which for some strange reason, this is just, the convention, don't blame me, it's the 75th percentile for a standard normal. Okay? Another way to write all that is z sub 0.25, z sub 0.25, because this 0.25 is downstairs in the subscript. So you can get these numbers pretty easily with your calculator using this inv-norm command. Inv-norm, okay, it's in the distribution menu right there with normal CDF and binom PDF and binom CDF. A couple ways you can do it. You can put in the area to the right there in the argument and slap a negative sign on it, or you can keep it positive and put in the area to the left. Okay, the calculator wants the area to the left, so it's sort of more natural, right? If you wanted the 75th percentile, then you do INV norm of 0.75, because in this case our alpha is a quarter, it's 0.25. Okay, or you could put in 0.25 because this thing is symmetrical, right? INV norm of 0.25 would find the 25th percentile. The 25th percentile is going to be about there. Okay, this is the 25th percentile. 25th percentile. Okay, so if you find that, the 25th percentile, multiply it by -1, you arrive there. Okay, by symmetry. It just flips it the same distance from 0 to the other side of 0. Okay, so either way you want to do is fine. Let's do some examples. Find the following with your calculator. Also mark the locations of the z-scores beneath those density functions. Okay, so yeah, let me get a normal curve here. This is a standard normal curve. Okay, so the mean is 0 and standard deviation is 1. Okay, it says z sub 0.025. 0.025. Z sub 0.025. I'm looking for the mark. What is this? Let's translate this into English. This is going to be the, can you do it? It's the what's percentile. Very good. 97.5. Bet you didn't know that was a word. 97.5 percentile. Okay. I get it with my calculator. Either way, I could do it INV norm of 0.975, or I could do negative INV norm of the area to the right, which is the 0.025. And pull out my calculator, and again, this is in the distribution menu now. Second vars, see the DISTR right above the vars key there. It's right below normal CDF, INV norm. Okay, option 3. It wants your calculator, confusingly, it wants the area to the left, right? No, left, right? No, you know what I mean. It wants the area to the left because it wants to give you the 97.5 percentile. Okay, I can put in my mean and standard deviation there. If I'm working with a standard normal, then they are 0 and 1 respectively. So you do that. There it is. It's 1.96 approximately. 1.96. Okay, so now I could come up here to, let's see, 1.96 is about there. Okay, so I know that this area here in blue is about 2.5%. This area over here is 97.5%. And this mark right there, this is about 1.96. That's what we're doing here. We're trying to find the location. Where do we draw our knife through here to lop off the upper 2.5%? Cleave it off and away from the lower 97.5%. Let's do another one. Z sub 0.05. Okay, so what percentile is this? Z sub 0.05. This is the 95th percentile, right, for a standard normal. I can get it with my calculator by doing INV norm of 0.95. Okay, if I don't put the mean and standard deviation there, then it knows that I've got a standard normal, or I could, put them there like so. Or again, by symmetry, I could just do I and V norm. That is by the symmetry of the distribution, right? It's symmetric here about this line, right? 0.05. I can just put the number in the subscript right directly in there and then slap a negative sign on there and I'll get the same answer. Okay, let me show you. I didn't do it that way last time for the other one. I'll do both ways this time with the calculator. So if I do INV norm of 0.95, I get 1.64 something. Okay, also if I do negative INV norm 0.05, then I get the same thing. Exactly the same thing, 1.645 approximately. So if I go to about 1.645, that's about here. This area here is 5%. This is 95%. The stuff out here in this white area here is 95%. And this mark is the 95th percentile, and we found it. It's 1.645. It's the 95th percentile under a standard normal. Why don't you try the last three on your own? Why don't you pause the video and see if you can do these. Okay, I'm going to work through these now, so if you haven't paused the video and tried them on your own, then maybe you want to go ahead and do that. Z sub 0.5, Z sub 0.5. What's another way to say that? Z sub 0.5. Oh, we're looking for the 50th percentile, right? What's the 50th percentile? Oh, I know just by looking at it, right? It should be 0, right? Z sub 0.5 should be the 50th percentile. Okay, I didn't get this directly from this, but I know that this number down here corresponds to this 50%. So that means then that I've got 50% over here, and so 0 must be the 50th percentile, right? Okay, because 50% is to the left. Okay, so I'll get that by doing INV norm of 0.50. Or if I do negative INV norm of 0.50, I should get the same thing, right? Yep. And in fact, if I use my calculator, then second vars option number 3, 0.5, I get 0. Good. Okay. If I do negative of that, I also get 0. Okay. Negative 0, 0. Okay. Good. So that all works out. How about the next one? Z sub 0.975. Z sub 0.975. Okay, so this is going to be, okay, and what we're saying here is that the area to the right of this mark is 97.5%. So this is the 2.5 percentile. So I can do that with my calculator by doing INV norm of 0.025 or negative INV norm of 0.975. And either way, I should get the same thing. So I'll just insert a 0 and a 2 there. Okay. Negative 1.96 approximately. Negative 1.96 approximately. So down about here, right? What this says is that, I've got about 2.5% out here, about 97.5% up in here, running off to the right. And that this mark right here is negative 1.96. That's the 2.5 percentile. Hey, we've already seen this 1.96 number. Remember before when we found the 97.5 percentile? It was up here. Okay, remember this mark was 1.96 positive. 1.96 positive, right? By symmetry, yeah, that sort of makes sense, right? If I've got 2.5% down here, then over here in red, over here I've got 2.5%. Okay, so then how much now is in the middle between these two marks? I got 2.5% out to either side. Now I've got 95% in the middle there, right? The 97.5 percentile is still 1.96. But if I go 1.96 standard deviations, the standard deviation is 1 in this case, right? If I go 1.96 standard deviations, or just 1.96 up or down from 0, then and what? I've got about 95% right there in the middle between these two marks, and 2.5% out to either side there. See that? Hey, remember by the empirical rule that if I went out two standard deviations, I'm at 95.45%? Well, here we're not going quite 2 out. We're going just shy of 2. We're going 1.96 out to the left and right. So we'll have just a little less than 95.45%. We're at 95%. Okay, so this sort of matches up with the empirical rule, doesn't it? Got 95% between negative 1.96 and 1.96. And finally, z sub 0.62. Let's just do that with our calculator. Z sub 0.62. That's INV norm of 1 minus 0.62. Okay, or 0.38. That's INV norm 0.38. Or if you want, you could do negative INV norm 0.62. And what do we get there? Let's see. INV norm 0.38, negative 0.3055 approximately. Okay, let's see. Does that make some sense? Let's see. We're looking for the 38th percentile. So yeah, that should definitely be negative, right? If I look at my graph here, the 38th percentile is going to be, down around in here somewhere. According to our calculation, it's like, it's like right there. Okay. Negative 0.3055 is the 38th percentile. I got 38% in there. And then the rest of it, 62%, is off to the right. So this number equals z sub 0.62.